All right, welcome. This is going to be a quick lesson covering over what we did for transformations. So transformations are a way of changing a known graph to make it kind of like be a different graph, to be a different function. Because we have these 5 parent functions we've been using: linear, quadratic, exponential, rational or reciprocal, and square root or radical. We have these 5 parent functions, and these are very useful. And we see that, like, especially with the linear one, we've done a lot of stuff with linear functions, not just in this unit, but in previous units and previous years as well. So we have this function like y equals x. You've definitely graphed this at least a dozen times. But you haven't only just done y equals x. You've also done y equals 3x plus 4, where we have different values added to the function. That it changes how it looks, where x might look like this, but 3x plus 4 now looks like this. Actually, that doesn't really start at 4, but we see that it's just much steeper and it looks different. So these adjustments, you've done them already, but these are transformations. We're changing our function starting with a basic function, starting with a parent function. So let's look at a couple of examples and see what possible ways we have of changing these functions. So first off, let me actually use Desmos for this, so it's easy to see. So let's hide this for now. Get rid of those. And let's say, for example, I have f(g) of x is equal to I have x squared plus 3, and here's my graph. We see that my line is up here. And think about, like, what does my parent function of this look like? My parent function being x squared, we see that my original function, which is Zion, should be down here. But in actuality, my function of x squared plus 3 is up top. This is the first transformation, and it's called sliding or translations. So we have one way of changing how our graph looks, because also over here we see that we moved it up a bit. So transformations. First off, we have one, we could translate it. That's the mathematical term. What we're going to use for most of it is like we're shifting it. We're moving it around. Think of it like you just pick up the graph and just moving it up. Like if I had this quadratic, I'm just moving it now over here. Or I move it up. It still points the same way. It still looks the same, but now instead of being at 0, 0, for example, over here, we see that my curve, my vertex is at 0, 0. Now my curve, my vertex is at 0, 3. Not much really has changed. I can do this for now. We'll talk about this slider in a bit. We said I can just move it up and down, and the graph looks very similar because the shape lines up perfectly. The shape's not really changing. I'm just moving it up and down. So that is one. We could translate it. We could shift it. This moves up, down. But if we move it up and down, we can also move it left and right. So that is one way of adjusting it. So we'll learn more about how I'm adjusting it in a minute. But let's see, what if I do it like this as well? I can also move it left and right. We'll learn what these h and k's are in just a second. We see that my graph moves left and right. And also, if I have the square root function as well, it's the same exact thing. I can also move this function around. Up, down, left or right. So that's one, translations. Next up, what else can we do to make our graph look a bit different? One is, let's stretch it. Stretch / compress. So looking up here, once I get to y equals x or y equals 3x plus 4, my 3x plus 4, it doesn't look exactly the same. It's not like I just moved it up a bit. I turned it, or in other words, I stretched it. I picked up the ends, I picked up the top and bottom, and just kind of stretched it up. And now it looks like that. It looks the same now. But before, I was like down here, but I could stretch it up. But I will compress because we also compress it down and flatten it. But we also compress it this way, and we see that now my slope matches up. I could stretch it this way, and now my slope doesn't match up. Compressing and stretching, you have to be careful with the direction. Just like you have to specify up, down, left, right, you have to specify stretching and compressing vertically or horizontally. So stretching and compressing is another one. Let's see this now on Desmos, where I have this. So I have my graph right here. I could stretch it. I'm yanking it up. Don't worry about that for now. And I'm compressing it. I'm flattening it down. Stretch, compress. You could think this like a balloon, where I have a balloon right here. If I compress it one way, what happens to it is that all that air must go somewhere. So I compressed it, but it also stretched the other way. But also if I compress it the other way, it must stretch out. You can't just compress it all directions and not have any stretches. The last thing that we can do with a graph for now is reflect. We saw a little sneak peek, but now my reflection, if I shift it, I see that now I'm inverted. I reflected across the x-axis. There are many types of reflections, but for now what we're going to focus on is reflecting across the x and y axes. We're reflecting it. So think of the x and y axis like mirrors, and we just reflect. So I could reflect it like that, and then we just take the points that we have, and I'm up over here at positive 1.4. Then I go down here to negative 1.4. This just imagines that there's a mirror here and just reflects it on that. We also do it like this. Let me set this back up to 1. Where now my y-axis is my mirror, and it's reflected it. So we can now see these visually. One way that we could test this out and go through it is, let's try to identify what transformations are happening to my graph, because we don't need to worry about all this stuff for now. Let's now focus on what transformations are happening to my graph. So using this, using my square root function as my basis, let's set it up like as follows. Let's actually make this a bit simpler for now. So here we are. I started with the blue, the cyan, and now I want to end up at my white. What transformations happened to my graph? You might not always be given a cyan, but let's identify what our parent function is. Our parent function is, looking at the shape, we have a square root function because it ends at one point and it kind of flattens out. It still goes up forever, but it doesn't increase as much as it is increasing to the right. So I know that it is a square root. Next up, we want to identify what happened to my graph. Because my graph originally starts down at 0, 0. The square root of 0 is 0. The square root of 1 is not 4. So my starting point is not correct there. So to move my starting point to this point, I must shift it right 1 and then up 4 to end up right here. when you find transformations, when you try to identify transformations, think about key features. And a lot of times a key feature could be its origin point, where it touches origin. Most of our parent functions do touch our origin or touch some key points, except for these two. We want to see some key points, like where it touches 1 or where it touches the y-axis. Just there's some key points that you can identify and see where did that move to and how could I get that. So here we see that this one shifted right 1 and then up 4. So that'll be our answer. You can write down it shifted right 1, shifted up 4. Now let's see, what else can we do? What if now I take this function so now I have a line right here. I have a line here and I want to learn what happened to this line. So what might my parent function be? My parent function is probably just a linear function. I have a basic line. I want to graph my line and see how can I transform this line into this white line. So first off, what I could do is actually, my line is not crossing 0, 0. So where can I move it to a point? I can move it to the right to 1, 0. I'd be like, I moved to the right 1. So minus h. So imagining that this point right here, look at that point and see it slide to the right. We can think that, I slid my function to the right. Another thing you could think about is I slid my function down. So you could try to imagine it sliding down. You see that we slid it down. So we can slide it right or slide it down. Either way, when we get to this point, we see that we're not quite there yet. So the next thing we need to do is I need to stretch it up. I need to give it a vertical stretch. So let's go like that. And we see that if A was normal, like I'm not multiplying anything, I need to stretch it up. I stretch it up. That kind of moves this around. But now we can shift it over to make it line up. So what happened here is we stretched it up, stretched vertically. Then we shifted right. Or we shifted down. So this is one way that we will try to solve these problems. You will be given a graph and you will have to identify what transformations happened to this. Did we reflect? Did we shift? Did we stretch? Did we compress? And how we do it is find the starting function and then go step by step and see what happened to it. So that is one way we could test this. The other way is we want to go deeper into some of it. I don't want us to just list off, it stretched, it shifted, it reflected. I want us to actually know what happens, exactly what happened. So here's where this comes in. F of x equals a times x minus h squared plus k. This function is the basic function for transformations, but we're going to use it by focusing solely on quadratics. So that's why the square is here. Looking at quadratics, I know what quadratics look like. I know that it is just x squared. I know it looks just like this, with key points at 0, 0. I need to add another one at 1, 1, and at negative 1, 1. I have key points here. We also know some other key points, such as like 2, 4, and negative 2, 4. But I want us to get super comfortable that at least the first 3 we know immediately. The second 2, the fourth and fifth one, we can always get there. But you need at least 3 points to draw a curve, and the first 3 are the easiest 3 all the time. The vertex and the points to the left and to the right of it. These points are vital. So that's x squared. But now I have this big one right here, and I add sliders to them. So my graph, it looks exactly the same. It looks so much the same that it's overlapping. Because when a equals 1, I'm multiplying by 1 on the outside. That does nothing, because multiplying by 1 doesn't do anything. So let's ignore that. The h inside is subtracted, so I'm subtracting by 0. So x minus 0, that does nothing. So far this whole thing is just x squared. X minus 0, so just x squared times 1. So it's just x squared. And now on the outside, I'm adding 0. So at the basic value, if a equals 1, h equals 0, and k equals 0, this is the parent function. No transformation. You have to memorize these. Multiply by 1, nothing happens. Adding or subtracting 1, 0, nothing happens. These are a parent function. But the problem changes. What if my values change? What if h changes? What happens to my function? You see that h, if I go from 0 to 1, I shift it to the right. So if h increases, I shift right. If h decreases, I shift left. And this is very, very important. One thing that we want to notice is that we want to keep it as positive to the right, negative to the left. And that's why this negative is here. That negative, I'm subtracting h. So if h is 3, my function actually looks like, let me adjust this one, minus 3. We see that my cyan just lined up perfectly with it. That minus 3 right here is saying my h is 3. So be careful with h. One thing you can do is just negate the inside, aka h. So whenever you see a function written like this, and you want to find the h value, just get the value that is here and just invert it. I see my negative 3 right here, so now my h is just positive 3. If I see a positive 3 right here, I see a negative 3, so that means I'm to the left. That is what I mean by inverting the h. So if h is increasing, I shift to the right. If h is decreasing, I shift to the left. What is next? Let's set h back to 0, the default. Now I have k. I'm going to add something else. If k increases, I go up. If k decreases, I go down. Let's actually draw something real quick. If k is 2, actually I'll do this demo right after. So if k increases, I shift up. If k decreases, I shift down. And k is just normal, it's positive. I don't negate k. H is the one I negate. So let's say I have a function like this. H is negative 3, k is 2. What transformation happened? I shifted left 3 because I have a negative 3. I went left 3, and then I went up 2. And it makes sense because like right here, I have negative 3, 2. So I went from 0, 0 to negative 3, 2 because I went left 2 and then up 2. We can do that for every single point. I mean, oh, for negative 1, 1, it went left 3, so it's at negative 4, and up 2, so it's at positive 3. So we see that negative 4, 3 is a point here. But that is exhausting. I don't want to do that for every single point. So what we do instead is once you find your vertex, you do it for one point, your vertex. I can now find my left and right points because how I go from 0, 0 to my next to positive 1 to negative 1 is I just add 1 to my y value. That is what the quadratic function does. It's very simple. So let's see, I go to negative 4. I just add 1 to it. So negative 4, 3. I'm going to go to negative 2, so I write 1. I go right 1. It's a negative 2. I should probably end up at 3. Negative 2, 3 is right here. So what I did for translating my graph I went and I moved these points and I found my points for this new graph by getting my vertex, moving my vertex to the left and up, and going for my vertex to find my next ones. I'm kind of imagining that everything is gone and all I have, let's see, will this work? Yeah, kind of imagine like everything's gone and I just have a new axis right here. I'm going to imagine that this right here is actually 0, 0. And I'll go based off this reference. So this will actually end up being like my negative 1, 1. This is actually my 1, 1. And imagine my x and y axis starts right here. It doesn't actually end up like that, but that's what I'm imagining when I draw this. Let's delete that. And it is still these points, but that's what I am imagining. I just make my vertex and I plot it. So let's do one example real quick. What if I have the example like A will just be 1. Okay, so I have this function right here where A is 1, so it doesn't really matter. But I have x plus 2 squared minus 4. What is my h value? And what is my k value? So first write those down. Pause the video if you want to try doing yourself. But my h value, we said I have positive over here, so it must be negative. My h is negative 2. And my k on the outside, I have a negative 4. So I'm going to set these here for now. So I have f of x equals x plus 2 squared minus 4. We know a is still just 1, h is negative 2, k is negative 4. So what happens here? I know that since h is negative 2, I shift left 2. And since k is negative 4, I shift down 4. So to graph this, what I'm going to do, is I'm going to make a point. You could do this on paper. I'm just going to do it on this. I'm going to make a point at negative 2, negative 4. I have a point right here at negative 2, negative 4. I want to use this as my graph. So I moved my vertex. I shouldn't have deleted that. My vertex was at 0, 0. But I moved it left 2, then down 4. from this as my reference point, I'm going to add some more points. My quadratic, if I go to the left one, I add 1. So that should be a point on my graph. If I go to the right one, so I go to -1, I should also increase by 1. So I have my 3 points right here. Let's see if my curve from these 3 points ends up being my graph right here. It does. That's how we graph quadratics. We move our vertex, we list our transformations. Let's actually write this down. To graph our quadratic, to graph transformations, first off, we find A, H, and K. Next up, you list transformations, and they have a specific order. The order is horizontal shifts, which is H. Then you do your stretch and reflections, / reflections, which is A. Then you do vertical shift. So I did it subconsciously over here. It won't really matter for this course, but it's good practice to have this in mind. And then finally, what we do is we apply transformations to vertex. Then keeping transformations in mind, we find side points. So that's how we graphed it right here. I found A, H, and K. I listed my transformations in order. I apply my transformations to the vertex and the vertex alone. And then you find the sign points. Keep in mind the transformations. Let's do one more. Let's also see what A does now. What if A is not just 1? Let's change this back into H and K plus K minus H. It's still right there. But moving this back down to 0. Moving this back down to 0. If A is not 1, if A increases, I start vertically stretching. If A decreases, if it's less than 1, I start flattening out. But I can't say that just yet, because if A is decreasing, I get wider. If A is increasing, I get more narrow. Because once I get negative, something drastic happens. I flip it, and now as I go more negative, it gets more and more narrow. So stretching vertically again. So you have to be a bit careful with this rule. So with A, if the absolute value of A is greater than 1, rate of change increases. I stretch vertically. Vertical stretch. If the absolute value of A is less than 1, the rate of change decreases. Vertical compression. It flattens out. The next thing that we could do is we also see that if A is less than 0, if it's negative, we reflect over X axis. So A has a lot of stuff going on. All 3 things. H and K only do shifts. A does the other 2. They're more complicated too. So that's why I said find side points. I didn't say just plot more side points by doing the rule all the time. Because the rule gets a bit tricky when we start stretching it out and compressing it. It's not just +1 - 1 all the time. So let's do one example of this. And I think that we could probably finish it with this. So let's say A will be 0.5. So since A is now 0.5, I still want to list off what's happening. F of x equals 0.5 x squared. A is 0.5, h is 0, k equals 0. What is happening to my graph? It is vertical compress by 0.5, or by 1/2. Nothing else is happening. I listed my transformations. Now I apply my transformations to my vertex. So my vertex at 0, 0. I want to compress this down vertically. So I'm bring it closer to 0. If I squeeze from up top and down bottom, nothing happens at all. It just stays at 0, 0. But I know my graph must look different. So I'm squeezing it and nothing happens to this point. So now let's actually find my next point. So that squeeze is still happening. And if I'm squeezing by 1/2, by 0.5, we could make the assumption, the actual correct assumption, that my point will actually be here. My point, I add a slider here. It was at 1, and I squeezed it down and moved it halfway to closer. That's what happened. I squeezed it and moved it down. The other way that we could find this out, because knowing exactly where to move it to gets a bit hard. Knowing exactly where to move it to is we could plug our point, our value, one left and one right, into our equation. So if I have -1 and I want to plug it into my function, I want to find -1, so let's find f of -1. F of -1 equals 0.5 times -1 squared. 0.5 times +1, or just 1/2, or 0.5. We use our formula to find our points. We use it to find the one to the left. We use it to find the one to the right. And now our graph ends up being just like that. So as you do your homework, which is the rest of the packet, please follow these steps. List off your A, H, and K. Do your transformations. And especially if there is a stretch or reflection, test the points to left and right. If you're able to do the transformations in your head, if you're able to visualize the stretches, compressions, and reflections, that is perfect. But if not, please rely on the function. Because we do transformations, it's not like we're doing transformations just now, and then I'll expect you to memorize this for Math 3 and Pre-Calc. No, we're introducing it now so that in future classes, in future lessons, you have this basic understanding to build upon. That we have it here, and it's really good for memorization, really good for skill building, to introduce skills, different parts of different skills over a course of period of time, so that we could build upon it and it lasts longer, it's stronger for memorization. That's why we're teaching little bits of geometry, little bits of trig, little bits of transformations, little bits of functions every year. So good luck on your homework. Hopefully this is helpful, and I'll see you guys next week.